recording. Okay, I think recording's working. Okay, I do have some announcements to get here and then you can take over. Is this working? Oh, it's not. Okay. This seems to work now. Okay, welcome back to CS 198-126, Deep Learning for Visual Data. I do want to get through some announcements quickly. So we are going to have OH starting this week and Corey 531 and Corey 212 on Wednesday and Friday from 4 to 5 p.m. We had decided on an attendance policy. You should attend 70% of the lectures this semester. If you're going to give a pass to everyone for lecture 1, which was last Wednesday, but starting today, there will be 20 total lectures. You should attend at least 14 of them. And in case you do have to miss a lecture, we will post lecture videos online. Last week's lecture should be up. Sorry, there was a delay on our end. Quizzes. So quiz 1 has been released. It's due next Monday. It's going to cover content from last week's lecture and the 2 lectures from this week. We will try to get assignment 1 up as soon as possible. We're running into some delays. Sorry about that. We are hoping that it will be up by tomorrow night at the latest. Yeah, so with that said, I'm going to hand it over to Rohan for the lecture.
Hey, nice to meet you guys. Today's lecture is going to be pretty fast-paced, but there's a lot of resources online that kind of cover the stuff that we're going to be talking about. So we'll be sure to send out links or kind of give you ideas of where you can search for these resources afterwards. Yeah. Yeah, these will be weekly. We'll have people staffing it at these times.
Okay, will it be the same room?
Yeah.
So Corey 531 on Wednesday.
The 2 rooms are different.
Okay.
The 2 rooms are different, but we do have them booked every week. Yeah, as people start to fill in, we're gonna get started. So today's lecture is about kind of the motivations behind deep learning, so that we have a solid basis going into the kind of the state of the art and learning more about why it is that this is important. Today's kind of lecture is going to first cover like the basics of the math behind this, and then kind of motivate why this matters, and then kind of go through some examples of how a neural network works. Quick math review. So vector dot products. The dot product of 2 vectors, as you guys might have seen in some of your lower div classes, is the element-wise sum. And kind of being familiar with vector multiplication and the respective kind of implications of that is important for neural networks, specifically backpropagation and figuring out how a forward pass through the neural network works. We generally like to express everything as a form of either vectors or matrices, so that it makes it very easy to represent the kinds of things that we're multiplying as well as our data. We'll see data matrices often as many rows with different features that represent different columns, so that when we apply transformations, we can apply them to batches of data at a time. Representing things as matrices and vectors allows us to visualize that a little bit better, and especially when we go into things like transformers, this kind of notation is going to be very important to be familiar with. Matrix vector product. So when we take a matrix of weights, for example, and we multiply it with something X, we want to be able to calculate that product. And this is extremely important when we talk about what a neural network is, how it works, and how it applies transformations to data. You guys might recall from the last lecture that we're trying to fit a function essentially to predict what future data values will be or to classify existing data values. And through that process, we want to apply different transformations to try and learn this function. And we will be modifying this W matrix in the next couple slides and kind of showing how that process works as well. But a matrix vector product is multiple dot products where every row of the matrix is taken with respect to W. That dot product is then put into a resultant matrix. And I'm sure you guys are mostly familiar with this kind of stuff. There's a lot of linear algebra review online as well. Vector function notation. This is extremely important as things might get confusing when we start reading papers, kind of going into how different things play together for the state of the art in computer vision right now. X is usually an input vector. Y is the label corresponding to X. So you can think of this as kind of like a ground truth or a training label. We'll oftentimes have kind of like a truth Y that we use as our label, and then our predicted Y. And using those two, we can calculate some type of loss, which we'll also talk about in this lecture. W, B, or theta are parameters that we control. So these are things that are tunable or something that will change over the course of training a neural network. W is usually a matrix. In general, capital letters are matrices, lowercase letters are vectors. B is a vector, and theta is a set of parameters. So in this example below, you can see that a certain function, f, takes in x, y, w, b, and theta, and these are all being used in various forms. Now, you might notice that there's a subscript I, and what these represent are specific components or values of the vector, so that you could do an element-wise comparison or an element-wise operation as opposed to doing an entire matrix. So for example, what this does is it takes the W and X product, matrix vector product, and it takes the ith value of that, and it multiplies that with the ith value of theta and squares that. And so what this represents is a single vector, and then we're summing that over a single component or scalar value, and we're summing that over every single component of our result. This differentiation will become extremely important in the next couple slides. So in terms of taking the derivatives of vector functions, vectors are comprised of scalars, as we saw, so we should be able to take the derivatives of these. This is very important. There's many classes that talk about this, 127 and 189. Especially taking vector gradients and the entirety of vector calculus. As you can see here, we have f of x that we're setting equal to a transpose times x, and taking the derivative of the scalar function with respect to one of the elements in a parameter vector. As you can see, this expands to a1 times x1 times plus a2 times x2. Like we talked about, the dot product is just an element-wise kind of addition of pairwise products. And so when we take the gradient of this, we take it just as in calculus, right? The derivative of a to the x is a, the derivative of a t x in this case is ai, or the scalar partial derivative of a specific component, xi is ai, its respective ai. We'll touch on this a little bit more, and in practice, as you see more of these, you'll start to become more familiar with it if you haven't already taken a class. But in general, if you have something that maps, for example, like an ND dimensional vector to a 1D dimensional vector, that's something that we can take the gradient of. And then if you have something that maps an ND vector to another ND vector, then that's something you can take the Jacobian of. These will start to be more clarified as we kind of touch on this more in future lectures. So what is the gradient? This is a gradient surface in the bottom right, sorry, that shows several points on some type of surface that we're potentially trying to descend. This is a vector of the partial derivatives with regards to each function input. So in vector calculus, much like regular calculus, the direction of steepest increase in a function's value from a point is along the gradient vector. So we want to compute the vector gradient, and that's the direction or step that we want to take in order to minimize a certain function. There's a lot of, again, videos online on all of this content. The purpose of this lecture and the other lecture is to kind of motivate some of the things that are going to play into more complicated topics that we discuss, so that there's some math intuition behind how a neural network works, what backpropagation is, what is a loss, what is a gradient, things like that. Steepest descent is along the negative gradient vector. So by taking the negative of whatever your steepest ascent is, you get your steepest descent. If we want to go down a hill, follow the negative gradient evaluated at our current position. And when we talk about gradient descent, this will make a little more sense as well. You take a vector gradient, and then we take the negative of that and we multiply that to get the direction that we want to take a step in. And this is also the process of updating our weight matrices as well. Universal function approximator. So like we mentioned before, we're trying to create a function that either models future behavior or does something that we want it to do, right? In the future, we'll talk about different kinds of neural networks that have different kind of purposes besides maybe just classification or regression. But for now, these are some things that you can visualize in terms of examples. It's kind of hard to figure out which class of models work best for each task and data set. But hopefully by the end of this course, you'll be able to be familiar with what kinds of loss functions are used for regression versus classification. Are you using like cross entropy loss or using some kind of mean squared error, things like that. The motivation for neural networks. Yeah, our brain is able to do a lot of tasks. What if we try to create a model of the brain? Our brain has neurons, which is why this is called a neural network, where every node that we're kind of implementing in this network and training is able to make a decision itself, and those decisions combined are our final output. So we take in signals from surrounding neurons, and okay, so this is where things get a little bit more complicated, perhaps. But we want every neuron to be able to be connected to the neurons before it, take in prior information, and then make its own decision. And through this training process, we'll notice how different neurons have different weights assigned to them, and they're each making different decisions. Neurons output a signal based on the amount of signal taken in, that's their input, and the output as a function of the inputs is equal to something called a ReLU, or the weighted sum of inputs. In this case, ReLU is an activation function that takes this form. And as you can see, this is a really simple formulation. It makes a very simple binary decision. If the input is positive, then it outputs the input. If not, it outputs 0. So this is a very, very simple function, but it introduces some non-linearity in our decision-making process. Deep learning, while it does have some parallels to traditional cognitive science and the way our brain works, doesn't work exactly the same. And a lot of future neural networks that we'll talk about have potentially gone closer to modeling our brain, but kind of the vanilla neural networks in your first assignment and in this presentation aren't quite like that. A graphical view. So what is a perceptron? We want to weight each component of the input by some amount and then activate on the sum. So here we can notice that B is just a scalar being added to the weighted sum and is independent of the input. So our B's have nothing to do with our xi's, as opposed to our weights, which do take into account our xi's. This comes up with some kind of weighted sum formulation that is then passed into our ReLU function. So we've talked about our x's, we talked about our weights and our biases, which is what W and B are called. But how do these relate to each other to produce a final output? That's what we're gonna be talking about in the next couple slides. But a quick side note on ReLU is what we're using to make this final decision, or kind of bounding our input. So yeah, as you can see here, our W times X plus W times X for every component is then added to our bias term. And this is all being passed into our ReLU. So you can think of the ReLU as kind of the penultimate function before we give our output. So this is an example with ReLU instead of using kind of like a traditional function. So again, for notice, this is the ReLU function on the left here. On the right, you can see we have 3 input nodes, 3 weights, and 3 weights, and a bias term of -2. The math that we're doing here is we're multiplying our x's with our weights, and we're adding a bias term at the end, and then passing that output into our ReLU function. So as you can see here, we're taking x1, 3 times 3, our first weight, times 2 times -1, times 1 times -1, and we're adding our bias term at the end of -2. That's essentially how this works. And if you notice, this can be formulated like a matrix, especially if we have multiple weights that correspond to multiple x values, or if we have multiple weights where each weight is a vector and each x value is a matrix, where we have kind of different data points and different features corresponding to those in the columns. But this will hopefully become more clear with the next couple slides. This is another example that you guys can give a try to. If any of you guys want to try this example and shout out the answer. Oh, the answer, yeah. So yeah, this is what happens. In this case, you multiply our weights and our bias terms. We add our bias term at the end. Keep in mind that this result was negative. So when we pass it into our ReLU function, it'll take the max of 0 and -5, which is 0. So let's simplify this notation, and we can do this using the vector tricks that we learned previously, where we have a bunch of W vectors or a bunch of components of a W vector, a bunch of components of an X vector, and we're adding a bias vector. So we can take our weights and our inputs as vectors and our bias as kind of a scalar term that's added to all of these. Now, what if we have multiple perceptrons that share the same inputs? We call this a fully connected layer, where we have one input that maps to every perceptron, and every perceptron is connected to every input in some way. Neurons in the brain form these kind of connections, but again, this doesn't exactly parallel how our brain works. Each perceptron can be stacked into something called a layer. So you guys might be familiar with layers in neural networks, and that's essentially what this is doing. We have a bunch of inputs that correspond to a bunch of nodes, and they're all connected to each other. By stacking these perceptrons and multiple layers of these perceptrons, we form our neural network that can be trained and propagated through to kind of give a final result. To calculate the output of a layer, we stack each individual perceptron into a vector so that we can utilize some of the tricks we learned earlier, specifically being able to take kind of like a weight matrix, multiply this by an input X, add our bias term, and then pass that result as the X into our next value. So you can think of this kind of like a chain, and these similarities to a chain are going to become more and more clear as we go into more deep learning concepts. But ReLU is applied to each perceptron output independently, so it's not the entire thing combined. Instead, we can think of this as taking our first weight component, multiplying it by our X and our first bias term, and taking that entirety in its entirety as a vector and multiplying or applying ReLU to that. Each row is simply the perceptron equation that we talked about earlier with our previous examples for an independent perceptron. So each of these corresponds to the decision that a single perceptron is making, where it's taking a weight, multiplying it by an input, and it's adding the bias term as well. So each of these perceptrons you can think of as kind of training independently or coming up with its own independent decision. If we stack the bias terms into a single vector, we can write everything in matrix vector product and vector addition terms, which is the most compact form of writing a layer. So instead of applying ReLU to a vector where each component of the vector is the perceptron equation, we can take out the weights of that and make our weights a matrix, and kind of like abandon this stacked view and instead kind of think of everything at once, where you have a weight matrix of all of your weights that correspond to perhaps different features or different inputs, and then we multiply that by our input, which is X, and we add our bias vector. So in this case, our function now only takes in X, it takes in a weight matrix, and B, where X is our input. It applies the weight matrix to X. So for example, if X is a column vector that is n by 1, and our weight matrix is some like n by n matrix, the result for that will also be an n by 1 vector. And we can add our bias term to that, our bias vector to that, and we have a result. Keep in mind that this bias vector is just the individual biases that we had previously added stacked together, and our weights are all the previous weights that we had before, but now in a matrix, so that we can apply this kind of to all the inputs in one batch operation. This is shorthand to make it easier as we go into more complex examples. So what is a neural network? On the bottom right, you can see that this is a multi-layer perceptron because we have an input layer, we have a hidden layer, just like before, but these hidden layers are also connected to two output nodes, which could, for example, represent two parts of a classification task. Note that we don't activate with ReLU on the output layer. That's something just for the intermediary layers, but we can apply different functions to the output layer to get the kind of result that we want. For example, if this is a classification task, we might want to push some values towards 0 and some values towards 1. So if this, for example, the top node represented the probability our picture was a dog, the bottom node represented the probability that our picture was a cat. If the top node was 0.9 and the bottom node was 0.1, we could say with some certainty that this picture, based on the network's output, is a dog versus a cat. So we want to, for example, do these kinds of operations that aren't just the kind of binning that ReLU does. So each node is just a perceptron that we talked about before, and each perceptron layer is called a neural network layer. So we call this the input layer, the hidden layer, and these are the output nodes. We can choose to stack an arbitrary number of perceptrons at each layer or cascade it with an arbitrary number of layers. This has some implications in terms of the training process, in terms of how long it'll take to train, how many parameters we need to update, and things like that. But each layer can have a different number of perceptrons. So I could have another hidden layer after this with 4 perceptrons that connects to my 2 output layers, which may be conducive to learning some new information. The middle layers are often called hidden layers because they're not interpretable. These are usually like randomly initialized and then trained. We still choose to use the ReLU function for each layer for now. We're going to talk about different activation functions, which is what ReLU is called, as we go through this course and learn different kinds of architectures. But for now, we're using ReLU in intermediary layers, but not our output layers. Yeah, so as you can see here, we have 2 input nodes of -5 and 6. We have weights and biases associated with each node, and we have some kind of output. There's no ReLU for the output, but we are applying ReLU at each node. We don't want to limit the output range of our node. If it's negative, that might be something that we're interested in. And the perceptrons in the middle have fewer weights because they have fewer incoming connections. Notice how each perceptron in the middle has 2 incoming connections. Our output kind of takes information from all 3, so it has 3 weights for each connection that comes in. So a quick review of how we got here. This looks a little confusing, but breaking it down, this is our perceptron equation. We take our weight, which is a vector, and we multiply it by our x, which is our input. That gives us some kind of like scalar value that we can then add our bias value to. Now, taking into account that we have a bunch of weights for our different perceptrons in our neural network, we want to put our weights into some kind of matrix so that we can do a batch multiplication operation between all of our inputs that are in X and all of our weights that are in the matrix W, and we add our bias term to that. We can stack perceptrons and apply ReLU to those, where ReLU is some kind of activation function. In this case, it's simply the max of 0 and the value itself to ensure that we have no negative values. And as you can see here, this is the same picture that we talked about before, where we have some nodes that are connected to some perceptrons. This is considered a layer. And we have some constant inputs that are multiplied by our weights, added our biases, and we're essentially taking a weighted sum at each node. This is the final kind of function that we ended up with, where we take in an X inputs, W matrix of weights, and our bias term. I can stop for maybe like a little bit, just 30 seconds to ask if there are any questions real quick. Yeah.
You use ReLU for the input?
No, so we're using ReLU at the end of our matrix calculation. So this is for hidden layers, and in our output layer, we might choose a different kind of function depending on the kind of output that we want to get. Yeah. All right. Moving on real quick, we can cascade these layers or kind of stack them to form the full neural network, and we choose the dimensions of each matrix to get the right size layers that we want. So we want the dimensions of our W to include, first of all, the number of kind of input values that we have, or the size of X, but also include the number of nodes that we have, or the size of our hidden layers. The width has to equal the size of the previous layer because that's how many inputs we're taking in, and the height of W is equal to the number of perceptrons we're stacking for this layer. And implicitly, this kind of makes sense. We can draw this out after class if you guys still have questions about the dimensions of W. So what is wrong with abandoning ReLU? Without ReLU, we're kind of using one giant layer. And we can talk about this a little more later, but we'll move on for now. Classification. This is the task where the output is a vector, where entry I is the probability that an input belongs to the ith class, right? So classification, going back to our dog and cat example, our output, if we say the top node is the probability that we have a dog, the bottom node is the probability that we have a cat. This kind of bimodal output is what we want to get. And we can treat these as the two probabilities that are images of dog versus a cat. This means that we want to enforce two rules. The output of the final layer is between 0 and 1 because this is a probability distribution, and all outputs sum to 1. Our network outputs right now can be in any range of -infinity to +infinity, and we want to limit this. So we need some operation or function, kind of going back to your question earlier, what is a different kind of function that we can use to limit this output to 0 or 1? And the answer is softmax. The actual formulation isn't that important, but first we make all vector entries positive by taking e to the power of the certain vector. And if you guys maybe remember how the E curve looks, we can then divide each entry by the sum of all exponentiated entries to ensure that the sum of all entries is 1. So we're essentially normalizing these to make sure that their sum is equal to 1. And by taking e to the power of this, we're ensuring that they're positive values. The largest entry before will be the largest probability, simulating a hard maximum while being differentiable. We'll talk about why being differentiable is important later, but what we're essentially doing is we're taking potentially infinitely bounded values and we're making them, with respect to each other, maintain the same magnitude, but overall be contained between the values of 0 and 1. It also fills our need to turn any vector of numbers into something that can loosely be interpreted as like a probability distribution. So a quick recap, our perceptron takes in a number of inputs and does an operation of weighting them, adding a bias, and then applying a ReLU activation function in the middle layers. Neural networks are stacked perceptrons. We remember the perceptron equation that we started off with for each of these. We're essentially stacking them in a layer and then stacking multiple of these layers to make a neural network. And if you want to do classification and enforce that our model has valid probabilities at the end, instead of ReLU at the end, we want to use something called a softmax function, which pushes our values towards 0 and 1 while maintaining their respective values, kind of magnitudes, sorry. Aryan will now take it away with what gradient descent is. And yeah, feel free to ask any questions.
It's like before we move on, does anyone have any questions about the previous section? Yeah.
Wait, so you take a softmax for the power of like a really big, it's like a really big X type number. It's still like really big, right?
Right. So you can run into those kind of like issues with like underflows and overflows. Like if you have a really small number, then e to the power of that is going to be like a very small number, just like close to 0. But if you have a very big number, then exponentiating that is going to give you a very big number. So you can run into issues like this. But it turns out that whatever software you're using to like code this stuff is probably going to handle that by itself. So you don't have to worry about this on your own. Okay, so now that we learned about how neural networks work, let's see how to actually train them. So in the last lecture, we talked about how the weights of a model are optimized, are found by optimizing some sort of metric. And no matter what model you're optimizing, you would need some metric to optimize for. And one way we can define this metric is how poorly a model is performing. So we might say that, hey, if this metric is low, the model is performing really well, it's giving you a really low error. But if the metric is really high, then the predictions are not good. The model has a really high error rate. And ideally, we want to sort of minimize this error rate as much as possible. One thing that we're going to enforce, though, is that this metric, which we also call a loss function, is differentiable. And you will see why in just a minute. So one really common metric that you can use, a loss function that you can use, is MSE. We sort of touched on this last time as well. But the idea is that if you have your model predictions, say y pred I for some input xi, you can take the squared difference between the prediction and the actual like ground truth label, and then you can average this for all samples in your training data set, right? Based on this formulation, you can see that this number is going to be low if your if your predictions are close to the ground truth labels, it's going to be pi if they're, nowhere close together. So, this kind of acts like a good enough loss function. It's simple to use, it's simple to interpret, and it kind of gives us what we need, which is, it's differentiable, and it's low when the model is performing good, it's high when the model is performing bad. Any questions about, MSC before I move on? Yeah. So we're going to take a step back to this hill metaphor that Rohan sort of mentioned a few minutes ago. So imagine that you went hiking at night and you forgot your phone or something. Now you want to get back down, but there's like a thick fog around the mountain that you hiked up to. How do you get back down? You don't have a GPS with you. You can follow this very simple heuristic, which says that if I want to get back down, maybe I should just follow down the downhill slope. And it's possible that if I keep sort of repeating this process by just picking the direction that slopes down the most, I will probably reach the bottom of the mountain, right? I think that's a pretty reasonable assumption to make. If you were to formalize this using math notation, so imagine that you were to represent this hill as the output of some function, such that this function's out just like the elevation of the hill. You can find the downward sloping direction by just taking the negative gradient. So we just mentioned that the gradient points in the steepest, in the direction of the steepest increase of a function's value. So the negative gradient is going to point in the direction of the steepest decrease because we want to descend down this hill, right? It turns out you can just view your loss function as this hill, right? So your loss function takes in as input your function, your model parameters, and you want to decrease that loss. In one way, you want to walk down this loss hill until you get to the parameters that lie at the very bottom, right? Like maybe a valley in that loss function's like elevation map. And to do that, we can just take steps in the negative gradient direction. And we can take the gradient of our loss function because it is a scalar valued function with multiple inputs, and we know how to take the gradient of a scalar valued function. We just take the partial derivative with respect to each input and stack that into a big matrix or vector at the end, right? So if you were to view your loss function as something that takes in each component of a matrix, W as like the input, the gradient of that loss function is simply going to be the partial derivative of that loss with respect to each component of that matrix, which is then stacked into a vector or a matrix, depending on whatever the shape of that input is. Any questions before I move on, like how we are taking the gradients of a scalar valued function? Like, why does this make sense? Because this is a pretty important concept. Yeah. So the question is, what happens if we hit maybe a local minima, if we are like 100% down the hill? Yeah, so it turns out that's fine. So it might seem that, hey, I want to achieve this global minima for loss function, but it turns out that in practice, local minima is usually good enough. So even if you hit a local minima, when you're training like a big model, that is most likely going to give you the performance you want. Yeah, so even though global minima is desirable, you don't always need to hit it. Yeah.
Also for the bias, you also need to take the to put the bias back into the derivative of that result. Do you need to do anything with the bias, or you just need to do it with the vector?
So the bias is a vector with like multiple scalar components, right? So you're just taking the partial derivative with respect to each component of your bias.
So you also need to do the partial derivative.
Yeah. So you want to take the gradient with respect to every single parameter. It can be a matrix, it can be a vector, it can be 3D or 4D tensor, it doesn't really matter. As long as that parameter is something that can be learned, you're taking the gradient of your loss function with respect to it. I'm gonna skip this slide for now in the interest of time. But what this is saying is, when you're trying to find the gradient, you want to find the gradient at, say, a current position. So like when you're descending down a hill, you can only find the downward sloping directions at a point where you are standing, right? You cannot see the whole hill at a given moment, but you can see around you, and you can find the slopes at the point that you're standing on. The same idea sort of applies to gradient descent as well. When you're trying to find the gradient of your loss function, you want to find it at a given point, which is some set of parameters that you're currently working with. And based on this, we're going to update those parameters, and we will see soon as to how that's done. Turns out that these gradients are maybe not easy to achieve, but there is an algorithm to sort of get them. We'll talk about that on Wednesday's lecture. That algorithm is called backpropagation. But for the remainder of this lecture, just assume that some genie gives the gradients to us. So now that we have our gradients, we can step down this hill by simply updating our function inputs in the direction of just like gradient vector. Something that you also want to do is scale the gradient by some amount, say lambda. This lambda sort of can be viewed as how big of a step you're taking in the direction of your gradient, right? So if your lambda is big, you're taking a really big step down the hill, but if your lambda is small, then you're taking like teeny tiny steps. And this sort of step size ends up becoming a hyperparameter. It's called a learning rate. It's something that you have to tune for whatever models you are training. And here's sort of why it matters, right? So if you're taking steps that are too big, it's possible that you might overshoot the minimum, like the bottom of your hill, right? And suppose I were to draw a function that looks like this, it's possible that you might, just like keep ping-ponging back if your learning rate is too big, and we don't want that. On the other hand, if your learning rate is too small, then you're just gonna converge to the minimum, but it's gonna be very, very slow. And that's not really that great in practice, right? Because you're gonna be training your model for days or weeks, and that costs money. We don't want that. So it's something that you have to sort of tune, and you use something called the validation set for it. We talked about training sets, validation sets last week. That's sort of one of the functions. It's like selecting these kinds of hyperparameters that work well with our current model. So in the previous slide, we showed here the gradient descent equation for a single example in the training set, but you want to achieve low loss on the whole training set, right? Not just a single sample. If you remember back to how the MSE loss was formulated, you took the average of all the losses on each of the samples, right? So if you were to take the gradient of this average version of MSE, it turns out that's the same as taking the average of the gradient on each of those different samples separately. This is kind of a math fact. It follows from the fact that the gradient operator is linear. You don't have to understand what that means yet. You will probably encounter that when you take, say, math 54 or math 53. But regardless, it's something you don't have to like concern yourself with, because even if you understood the math behind this, some sort of software like PyTorch will just take care of it for you. But the issue with finding the gradient across the entire training set is the fact that our training set can be very big. So imagine that you are working with something like ImageNet, which has 1 million images, right? If you were to find the gradient across all 1 million images, that's not going to be computationally feasible. Something that you can do is find a happy medium. So like instead of just picking like one example or picking the whole data set, you just pick some value in between. So you just take like chunks of your data set, and these chunks are going to be of size, say, they're going to be of size that we call a batch size in machine learning literature, right? So if you were to take like huge chunks of your data and take your gradient descent steps along with these chunks, that's probably going to approximate what true batch gradient descent looks like, and that's really good enough for our purposes. It does, however, mean that the batch size that you pick ends up becoming another hyperparameter that you have to tune, like along with your learning group. Okay, so Someone, I think, asked a question like, why do we use a ReLU? You don't have to. Turns out there are many functions you can use. One common function is, I guess like it's not common anymore, but one function that people used to use is something called sigmoid. It spits out a value in the range 0 to 1, no matter what input you feed it in. There is a version of, are we running low on time? Oh, yeah, we still have time. Okay. Another version of this is called hyperbolic tangent, which is sort of like sigmoid, but it spits out a value in the range -1 to 1 instead of 0 to 1. There are versions of ReLU, like leaky ReLU, and GLU. GLU is something that's used in something called transformers, which we will get to in a few lectures. But in practice, we usually just end up using ReLU because it's very cheap to compute and it works well. It's good enough for our purposes. Any questions about activation functions? Something that you have to note is that activation functions should be differentiable. So ReLU technically is not differentiable at the point x equals 0, but that point, the probability of feeding in x equals 0 to a function is so low that it's fine in practice. So you should be differentiable almost everywhere. If you're not differentiable at a few points, it's fine. But you should you should pick activation functions that are differentiable, so you can find the gradients of your inputs, right? So MSE is not the only loss function you can pick. MSE is like a very easy one to use. It's like it has like a nice interpretation, and you actually do use MSE when it comes to like regression tasks. But if you want to work with a classification task, you want to use something called cross entropy loss instead. We don't have time to sort of delve into what cross entropy is, but I will encourage you to Google binary cross entropy and sort of like look at it in your own time, so get an idea of what it does. And finally, we get to this idea called regularization. So when we update our parameters using gradient descent, we don't really have too much control over what kind of parameters we end up with. So it's possible that if you end up with a really big weight matrix, it might not be desirable. And I also have a weight vector example. So suppose we have a function that takes in as input, some vector x and some weight w, and the output of this is simply the dot product between them. Right, so we will just treat w as sort of a weight, and you can treat x as our actual input. Now, what happens if you change x slightly? Our function value ends up becoming x plus like small change in x, right? And what would the change in the function value be? So if this is our new output, we subtract the original output, and this is basically how much our output changed by when we change the input x, right? Turns out that this is bounded by this value. It's the inequality here is called Cauchy-Schwarz. You have seen this in your algebra classes. But the idea is that even if you make a very small change in your input, if you're making it, you see that big, your change in output can still be huge, right? So in a sense, your model is very sensitive to the kind of data it sees. Yeah, makes sense.
Last time.
Oh, this is taking a norm of a vector. The norm can be thought of as like the length or the size of the vector. Right. Yeah, so if your model ends up being very sensitive, it is possible that it's only going to perform well on the examples that it has seen in the training data set, right? If you were to show it some unseen example, it's possible that if that example is if there's like a small change between the example in the unseen data set versus the training data set, you can still produce like a big change in your function outputs. So in a sense, your model is only performing well on the training set, which means it has overfit, right? We don't really want that. We want our model to perform, to like generalize to unseen data as well. So it turns out that we don't really want like huge rates. And something that you can use to discourage huge weights is something called weight decay. We will learn about weight decay in the next lecture, but there are two ways to sort of achieve this. One way is to simply multiply your weights by some constant like 0.99 at each iteration of gradient descent. So the weights automatically tend to decrease in size. Something else that you can also do is add the size of your weights to your loss function, right? So remember, we are trying to minimize our loss function, right? If we also try to minimize the size of the weights at the same time, it's possible that we'll end up with a network that performs really well on the task at hand while having small weights simultaneously. This sort of penalty term is also called a regularization term. And this whole idea of different techniques that you can use to make sure your model doesn't overfit is called regularization, and we will see some of these techniques in the next lecture. So we learned about how neural networks are trained and what they are. And that's sort of what deep learning is, right? It's the study of sort of these neural networks. Why do people why has it taken off recently? So in traditional machine learning, we have this phenomenon called the bias variance trade-off, which says that if you were to, and I know that this is something that we wanted to talk about in the last lecture, but we couldn't get to it in time. All of that information is on the website, in those lecture slides. If you have any questions about the bias variance trade-off, do feel free to make a post on it. But the idea is that you want to achieve both low variance and low bias error. And that's hard to do, because if you try to make your model too big, you're trying to make it too complex. In a sense, it might just memorize the training data. And for a while, that's sort of what it looks like. So if you were to look at this graph in the right side, what this is showing is how the model performs as you increase its size. So if you start with a very small model, it might not be able to capture the data well enough, and we get a really poor performance. But as we keep increasing the size, we are able to model the data better. But if we keep increasing the size even more, it's possible that our error rate might go back up again, because at this point, we're just memorizing the data instead of learning anything from it. And traditional statistics would predict that if you keep increasing the size, your error rate would just keep going up. But that's not really what happens in practice. It turns out that if you keep increasing the size, your data's error tends to go down again. And this phenomenon is called double descent, because you descended the first time and you're descending again. No one really knows why this happens. This is a very active research area as to why deep learning, scales so well. You might have seen these new models called LLMs, GPT-3, and you might have seen that the bigger they get, the better they perform, right? That's sort of this exact reason. For some reason, neural networks tend to perform even better when you increase their size, though no one can tell you why. Oh, yeah, this is just a meme I included. The idea is that traditional statistics viewed that maybe you should do some more analysis, you can't just add layers willy-nilly, but modern ML is just create what traditional stats says, we'll just make the model bigger, model size go per, and it just ends up performing well. Yeah, so that's sort of it for this week. We will talk about some more deep learning building blocks next week. Do you want to mention that we have a lecture attendance form that you should fill out? And yeah, if anyone has any questions, I know that I kind of sped through the remaining content really quickly because, yeah, this is just a large lecture slide. We'll keep this in mind for the next few semesters. We should probably break this down into smaller ones. But yeah, if anyone has any questions about any of the content that we just talked about, feel free to ask them.
There going to be any office hours?
Yeah, so there will be office hours on Wednesday, 4-5 and Corey 531, and Friday, 4-5 and at Corey 5 at 212.
So lecture number 1 or 2?
What's up?
Lecture number 1 or 2?
This is two, yeah.